Good morning. Today, our goal will be to measure the internal resistance for a battery. So let's commence operations. To do this, we are going to first explore some of the key terms and theory. When we measure the voltage or the potential difference from one end of the battery to the other, we'll refer to this as the terminal voltage. The symbol we'll use is V. The model that we'll be using for the battery consists of two key components. The cell. The voltage of the cell is called an EMF, the electromotive force, and it's measured in volts. The symbol we'll use to represent this is the Greek letter epsilon. In addition to the battery consisting of a cell, we'll also model the battery as consisting of a resistor. The symbol we'll use for the resistor is R, and R represents the internal resistance for the battery. It's measured in ohms. And so this is our objective today, to measure the internal resistance for a battery. And so to do this, we have to explore the connection between terminal voltage, V, EMF, epsilon, and the internal resistance, R. Here is an equation we're going to use to ultimately determine internal resistance. Terminal voltage equals the EMF subtract the current multiplied by internal resistance. Or V equals epsilon minus I representing the current, times R, the internal resistance. So before we continue, does this equation make sense? Well, when the battery is not connected to a load, for example, it's sitting on a shelf, we know the current is exactly zero. If the current is zero, that term disappears. Therefore, the terminal voltage is equivalent to the EMF, or V equals epsilon. Does the negative make sense in the formula? Let's see. So initially, we've set up our circuit so that the current is zero. It's zero because the load is not connected. Notice our reading of voltage, 1588 millivolts. So in a moment, I'm going to connect the load to the battery. Current will begin to flow. And the question is, what happens to the terminal voltage? Let's see. Notice the voltage dropped to 1516 millivolts. So the negative makes sense. The negative makes sense because the moment we had some current, the overall voltage at the terminal dropped. It dropped from 1588 when there was no current, when the load or the resistor was not connected, to 1516 millivolts. And so throughout this experiment, we will assume the internal resistance is constant. Resistance, of course, is calculated by measuring potential difference and current. So the multimeter circled there is set to measure potential difference, or voltage. Notice the leads of that multimeter are placed in parallel to the battery. The maximum voltage setting for this multimeter is 2000 millivolts. The second multimeter is set to measure current. The leads are placed in series with the circuit. And we've set the multimeter to read a maximum current of 200 milliamps. There are two more key components for this circuit. The resistor. Why is there a resistor? Well, the resistor will prevent a short circuit from taking place. It prevents too much current from flowing. We also have this component here. It's called a variable resistor. The resistance can be changed. It can be changed by rotating the shaft either clockwise or counterclockwise. So why do we need a variable resistor? Resistance is calculated by measuring potential difference and current. So we just don't want a single voltage and a single current. Instead, we would like to have multiple data points. So the variable resistor will allow us to change the resistance of the circuit. In turn, this will alter the current flowing through the circuit, which will alter the voltage. Initially, this variable resistor is set to high resistance, which means there will be low current. We will rotate the shaft to decrease the resistance, and this will increase the current flowing through the circuit. So this is what the experiment sort of looks like. Going to pick up the variable resistor, going to rotate it so that I'm decreasing the resistance, and notice the current begins to increase. Also note what's happening to the voltage. That's the voltage across the battery terminal. Now I'd like you to copy out this table. Please copy the title. And today there will be 10 different batteries that we will do this experiment for. Please indicate the battery that you have been assigned. In addition to the table, I'd like you to complete this graph. I'd like a professional title. In other words, I want a detailed title. Now your graph is going to look something like this. I'd like a line of best fit drawn. I want you to calculate the slope with the units and the correct number of significant digits. And I also want you to calculate the y-intercept. Now, looking at this equation, remember this equation. V equals epsilon subtract I times R. Based on that equation, I want a sentence explaining what the y-intercept represents and what the slope represents, and it's connected to that equation. Here is our data for battery A. Please record the voltage, which is in millivolts, and the current, which is in milliamps. Notice that the current is increasing. It's increasing because I'm reducing the resistance in the circuit with the variable resistor. Here is the data for battery B. Notice the current is increasing. I am reducing the resistance of the variable resistor, which allows for more current to flow. Here is the data for battery C. Notice that the current is increasing. It's increasing because I'm reducing the resistance of the variable resistor. Here is the data for battery D. The current is increasing because I'm reducing the resistance of the variable resistor by rotating the shaft. Here is the data for battery E. Notice that the current is increasing. It's increasing because I'm reducing the resistance for the variable resistor. Here is the data for battery F. Notice the current is increasing. It's increasing because I'm reducing the resistance for the variable resistor. Here is the data for battery G. Notice the current is increasing. It's increasing because I'm reducing the resistance for the variable resistor. Here is the data for battery H. Here is the data for battery I. Battery I is a 9-volt battery. So now the voltage is no longer in millivolts, it is in volts. So please change your table heading from millivolts to volts. Notice the current is increasing. It's increasing because I'm reducing the resistance for the variable resistor. And finally, here is the data for battery J. Battery J is a 9-volt battery. Please note that now the voltage is no longer being measured in millivolts, It is being measured in volts. So for your table, please change the heading from millivolts to volts. Notice the current is increasing. It's increasing because I'm reducing the resistance for the variable resistor. I hope you've enjoyed today's presentation. Have a great day. Bye-bye.